Okay, so this is the problem in week 1 on page 33. So we have three vectors a, b, and u. So we want to decompose u into three vectors where u1 is parallel to a, u2 is parallel to b, and u3 is orthogonal to both a and b. So what we are talking about is here we have a and b on some plane, and here is the orthogonal vector a cross b, and I want to decompose my u to be following these directions. So u1, u2, and u3. So first of all, instead of taking projection on u1, u2, or a or b, we have to take a projection onto u3 because we have a plane which containing the vector a and b, and if you have a u vector like this one, you can always decompose your u into a component on this orthogonal direction and some component on this plane direction, because this plane which contains a and b is orthogonal to these vector, so we can decompose this u into two components by projection. So let's first take the projection. So I will give the idea how to get the u1, u2, and we will do this by Matlab again. So u3 vector is projection of u onto a cross b, and then what we left with is u prime, which is u minus u3, right? And we automatically know that u prime is inside of the plane containing a and b, so we can set this equation that u prime is a linear combination of a and b. So we find S and T. And other way to find this equation, because we have, by knowing that this decomposition is unique, is that you set your orthogonal vector a cross b as c. Okay, so I want this u1 to be some multiple of a, and u to be some multiple of b, and u3 be some multiple of c, right? So I want to find these coefficients s, t, and r. So what I need is a linear equations, system of linear equations. In other words, I want my u vector 0, 1, minus 1 to be, this is u in a column vector, to be equal to this matrix multiplication S, T, R. So if you multiply this row of vectors with this column of scalars, then you get this expression, the star one. Okay. However, we wrote these three vectors as column vectors. Okay, so in real, this ABC vector is the set of these vectors are actually 3 by 3 matrix. Okay. But that's fine, because what we are actually doing is we are talking about the linear composition of three vectors here. So how do we find this STR? We simply find inverse matrix of this 3 by 3 matrix and then multiply that inverse on both sides. So we get STR. So STR is inverse matrix multiplied with 0, 1, minus 1. So let's do that in Matlab. So first of all, I want to find a projection, but I will do that often. So let me define a function in the Matlab. So there are several ways to define a function. We already saw the definition of anonymous function, that's an inline function. But in general, when you're talking about the function, it's a function in the program. So when you define a function in the Matlab, in a script, you always have to put your definition of function at the bottom of the script. So this goes the most bottom of this script. So, and also when you define a function, always the grammar looks like this. So function and end. Okay. So some functions start from the word function and end at the end word. And also the function needs an input and output. So output comes here. So v will be the output. And function needs a name. So we're going to give a name as proj. Okay, proj for projection. And as an input, we need a vector to project and also another vector to project on. So I will say the vector we project on will come first, which is A, and we are going to put the view as the vector we are going to project. And how do we define our projection? So usually when you define a content of the function, you have to put the three spacebar or one tab indented line. So we have v is equals to dot of a and u, and divided by norm u, and then also multiply by a unit vector of in direction of a, norm a. And then also we need a norm u. So norm u cancels out, and we have two norm a. So we have this. Okay, so we are done. So most programming language requires to put a return something to give an output of the function, but in Matlab this already says that the v is the output. You don't have to return it. But if you don't define what v is inside of the content of function, then it spits a error message. So anyway, we already done that, and let's define our vectors 1, 2, 1, and b is 2, 1, 2. And let's define C again. So C is a cross of AB. So when you do this, because even though there is no assumption, AB are not linearly dependent, so they are pointing to different directions. So we can do the cross product to get non-zero vector, and U is also defined 0, 1, minus 1. And U3 will be projection of U onto A cross B, which is C. So this is our U3, and U prime will be the U minus U3. So instead of writing U prime, I put UP, because U prime represents the Matlab considers U prime as transpose of U. So don't use prime unless you know what you're doing. Okay. All right, and okay, so I want to find A and B, so S and T, which satisfies the need to find S and T for UP equals to S times A plus T t times b, right? So this is also linear equation which we need to solve. So you have two unknown variable, but each up, a, and b has three components. So if you determine if you use the two equation out of three, that's enough for finding the unique s and t. So in other words, since up, a, b are three-dimensional vectors, we equate the equation implies three equations. So this is our equation. UPSA TB gives three equations, but we need only two to determine S and T. So what we are going to do is just use the first two components of our vectors. So what we're going to do is that I'm going to use only first two components from 1 to 2. Okay, usually UP has component 1, 2, 3, but I only use 1 to 2, and S times A of 1 to 2, and plus T times B of 1 to 2. So in other words, this is the how it works. So 0, 1 equals to S times 1, 2 plus T times 2, 1. So you see, I only use the first two components of these vectors. Sorry, I don't know what UP is, so yeah, let's put it as 1 to 2. Okay. So this can be also written as a column vector instead of these row vectors. So UP 1 to 2 column transpose. So these UPs, since ABC are defined as row vectors, I need to put a prime symbol to make it as a column vector. So this column vector is equals to 1, 2 prime times S plus 2, 1 prime times T. So I also have to use make these vectors as a column vectors. So in other words, this is the same. UP 1 to 2 prime equals to what? 1, 2, 2, 1 times so 1, 2, 2, 1, right? Yeah. So times ST. So let me write that in the board here. So confusing here. So we have U prime, and what I wrote just now is this one, A, B, S, T. But if I use the three components of these vectors, then this becomes 3 by 1 vector, matrix, and these becomes 3 by 2 vectors, and this is 2 by 1 vectors, which is fine. The multiplication is well defined, but what we are left with three equations comparing each component of the left hand side and the right hand side. But we only need to determine these two unknown variable. We don't need three equations to determine two variable. We only need two equations to determine two variable uniquely. So I don't want the last coordinates, so just use enough to use only the first two components. So that's what I'm doing here in this code. So let's try to find out what this variable is. So st, so I'm going to put this variable as s times t, st column vector, which consists of unknown variable. So I need to take the inverse of matrix 1, 2, 2, 1, and then multiply with up 1, 2 prime. What? Why do I have this 2 by 2 matrix? So inverse of 1, 2, 2, 1 up. Let's see what up is. up is 3 vectors. Okay. Sorry, I forgot 1 to 2. Okay, yeah. So I got this vector. So above one is s and the below one is t. Okay. So let's see whether we actually done this correctly. So so if I take my u1 to be first variable, which is s times a, and u2 to be second variable times b, and we already done at u3. So let's see what u1 plus u2 plus u3 is. Here is, we have 0, 1, minus 1, which is equals to u. So we successfully decomposed our vector u desired way. So another way to solve this is, I already mentioned that you can use a matrix multiplication. So we have C, so I'm going to define my matrix A, B, C as a column vectors, and matrix A consists of these 3 column vectors. So you see, I put the comma, or you don't have to put the comma here between each vectors, because these are columns, okay, not row. So if you separate column, you always put the comma here. If you want to separate the row, you put the semicolon. So, and this is A, and the variable that we need to find, as I wrote in the solution, is s and t and r, and that should be comes in the column vector also. So variable is equals to a inverse. So when you put inverse of matrix, and this matrix is a square matrix, of course, then you can simply put a minus 1 hat here, represent an inverse, and u. Okay, I already defined the u in the previous code. So I put the u prime, meaning that this u should be transposed to the column vector. Did I use A, B, C? Sorry, C prime. I forgot to C prime. All right, well, let's probably changed. So let's put this instead of A minus 1. So yeah, here we have these coefficients. So it says that these are S, this is T, and this is R. So each of their variables are coefficients for A, B, and C. So you can compare that also. U1 is first variable times A, and U2 is for second variable coefficient times B, and U3 is third one. And let's see whether it's done correctly. U2, U3. Yeah, we have 0, 1, minus 1. Okay, so we are done. So you can do your homework now. If you have any question, please ask now. I can do this and explain again. Right. So let's look at the last part of the second week. Okay, so this part. So the last week we defined the differentiability of two variable function of the form z goes to f of xy. So how about we increase the number of independent variable of the multivariable functions? For example, if you have a function from Rn to R, so this is a real valued function, which means the value of function is the real number, but it requires n number of independent variable to determine a single value of the function. Then we define a gradient as a vector. So this is a vector, and it denoted by the inverse square, inverse triangle, and called a nabla. Okay. So, or in this case, nabla, it reads as nabla f, and the component of this vector is the partial derivative of function for each coordinate. So if you want a gradient at specific point, which means that I want the vector, specific vector at that point, then you simply take the partial derivative at that point. Then you get the specific vector. So in this notation, what it really means is the vector field, because we didn't specify to the point to define a vector yet. Now we have this gradient notion, and we say that f is differentiable at the point in this Rn space if and only if we have this limit goes to 0. So you see this numerator part is almost similar to the definition in this two variable function case. We have original function and we subtract that by, there's something missing here, so minus fx0 is missing, sorry. So I have to subtract that with this long expression, but I just shortened as a dot product. But if I write that as long expression again, so when this coordinate x goes to x0, the denominator part is simply the distance between these 2 points, and numerator part is the value of function minus the value at that x0 minus fx1 at x0 times x1. Okay, so I have to also put this x as x1 to xn, and x0 as, let's say, I need another expression, let's say x10 to xn0. Okay, so x1 minus x10 minus fxn x0 xn minus xn0. So I want this long expression, the ratio of this long expression, to be 0. So this is simple generalization of two variable case, because if I take n to be 2, then exactly the same as the definition of differentiability. So by the way, these numbers are actual numbers, but x1 to xn's are variables. Okay? So these parts are linear approximation of f. So if I put the parenthesis here, everything becomes positive. This is linear approximation of function at x0. Okay, so similar to the original definition, but now it becomes interesting when you also generalize to the most general form of multivariable function, which means that your value of function is not just the single value of real number, but it's a pair of real numbers. For example, if you have a function from Rn space to Rm space, then we say that we assume that each coordinate functions are differentiable, which means that I need an independent variable to obtain m dependent variable. So I put yi as a dependent variable, but each dependent variable, say yj, is a function, multivariable function on x1 to xn. So I will give a name for these functions determining yj as fj, and I'm assuming that these are differentiable. Okay. Then we can talk about the differentiability of entire function f. Now, before we talk about when it's differentiable, we have to talk about what is differential of this function. So let's say we're going to define our differential and denote it by df, and differential at the point x0 is a matrix. The size of a matrix is m by n matrix. So remember that m is the number of dependent variable, which is the number of row of differential, and n, which is the number of column of the differential, is the number of independent variable of the function. The reason why we took this size is that it's only because we usually take the vector as a column vector. So if you conventionally decided to use your vector as a row vector, then this m and n will be switched. But many contexts, in many textbooks, they use the column vector as convention notion, so we use this size m by n. So anyway, so we have a differentiable at this point if and only if the limit goes to 0. So the only difference here is that we switched our gradient to the differential, which is the matrix, and we also switched our right hand side to be not just the 0 number, but it's the 0 vector. Okay, it's because the reason why we took the 0 vector is that the numerator side, this numerator part, is a vector, because fx is n tuple numbers, and what you see here is it needs a little bit of interpretation that this is the multiple of matrix of size m by n with a column vector, because x minus x0 is a subtraction between two vectors, and we conventionally use the column vector instead of row vectors. This is nothing but x1 minus x10 up to xn minus xn0. So then this is n times 1 matrix. So if you multiply these two matrices, then we get m by 1 matrix. Alright, and we subtract this m by 1 matrix with the value of function xf, which is also consists of m tuple numbers, which can be considered as m by 1 matrix. So that's why we have a 0 vector on the right hand side. So you see, these are actual generalization of the gradient vectors, which because if you think about this differential, look at this columns. these columns. So let's take the first column here. Well, what we have is we are taking apart. It's a little bit. So x1, xm, so 1 to n. Oh, sorry. So I have to take the row vectors here. Sorry. Yeah. So when you look at the row vectors of this differential, then these are the nothing but same as the gradient vector of the function f1, right? So this one is gradient of f1 at x0, and so on. So you can rewrite this this one as gradient of f at x0 and up to gradient of f1 to m of x0. Okay. Right? So when you rewrite this, fx1 up to fm x0, and then multiply with this vector. So let me switch back to our original notation of vectors here. Then what we get is we are actually taking a dot product between these vectors and these vectors. So what we have is f1 x0 dot product x minus x0 up to fx0 dot product x minus x0. So you see there's something wrong here, so it's actually, oh, maybe, sorry, so x0 x minus x0 x minus x0, when x is 0, y minus y0. Right, so I also need this minus, sorry, so minus of x0 here. I forgot to put this. Yeah, so, right. So this part, the red part, becomes the vector of these expressions. So you see these expression is, if you combine with the value of f at x0, this is the linear approximation of fi at x0 if you combine it with the value of fx0, fi x0. Okay, so you simply take the n number of value of functions and then linearly approximate that function fm or fj at the point x0, and if everything, the ratio of everything goes to 0, then everything's fine. So you have a differentiable function. So when you have a function, a general function, it's rather complicated to check whether it's differentiable or not. However, most functions that you're going to see in this course will be consist of a polynomial or exponential functions or sinusoidal functions and so on. So those functions are automatically differentiable unless you have 0 on the numerator or something weird like infinity happens. So you don't have to worry about whether the given function is differentiable or not. What you have to remember is that the differential of multivariable function is not a slope or not a number or anything, but it's just a matrix. So here's one more remark. Let me write that and then say it again. So when you have a multivariable function, the general form, this is m by n matrix. Now, if you want to find out the differential, you need a point which defines your differential. So without point, you cannot define a specific matrix consist of real numbers. However, you can also define your differential as a function which sends a point inside of Rn space to the matrix, the set of matrix of size m by m. So usually we denote it by m and n, and actually that's equals to r m n. Okay, so when you do this, you kind of thinking about your differential df as vector fields, because matrix is a vector where df sends a point to the matrix, which is the vector. So it's a vector field. So when people talk about the differential, sometimes, so if they just think about talking about the differential, they might think about the vector field of this vector field in this sense, or they're talking about the differential at some specific point. So if there's no ambiguity, it's okay to say just differential, but in principle you have to talk about differential as the vector field, or differential at specific point to define a specific matrix. Okay, and again, the most important thing to conclude this week's slide is that the differential of a function, including single variable function, is matrix, and therefore a linear transformation. Sorry. So if you finish this course, this is the one of the sentence that you have to remember end of the course or way after you finish this course. The differential of a function is a linear transformation. In other words, linear map. So in the high school, you learn that the differential of a function is a slope, but the slope actually is a map. It's a map which sends the speed of x direction to the speed of y direction. If you have a point moving along the x-axis at a certain speed, then if you multiply that speed with the slope of a function, then you get the speed of point in the graph moving along the y direction in that speed. So it's a map. The slope is actually a map sending x speed to y speed. How about the multivariable function? Why is the differential of multivariable function gives a map? Why is it linear map? So if it's a map, what does it maps to another map? What does it maps to one object to another object? So that's what we're going to talk about in our week, in this week. If you learn the chain rule. So to answer that question, we need a theorem called the chain rule. So If you have any question, please ask now. I will wait about 2 minutes. Okay, you have why the differential is linear transformation. A good question. So to answer a full, to give a full answer, we need a chain rule, which we're going to learn right now. But let's think about the single variable function case. Let me put a page here. So okay, so in the single variable case, let's say we take C as f prime x 0, so it is a slope of a tangent line. But what really slope means in principle is that suppose you have a tangent line here, but what we are talking about is if you have a point x0 and y0, and if you move your point x0, y0 from x0, y0 to the x direction by velocity vx, then your point on the graph also moves along the y direction. Your y coordinate also moves along the y direction. So this also moves in certain speed. Then vy is equals to vx times c, instantaneously, of course. So at that point, so C can be considered as a map which sends a velocity vector to another velocity vector, so fx, fy. So this is the set of this vector space, or vector space of x directional vector, and this is the vector space of y directional vector, which sends C maps this vx to vy, defined as C times vx. So it's a very simple observation, but that generalized to the meaning of geometric meaning of differential in the multivariable function. So in other words, if you think about the vector space of x directional vectors, there are only one directional vectors. Either you move along to the positive x direction or minus x direction with a certain speed. So all of this vx, vy maps is identical to the real number system. So I can rewrite this C as r maps r, So if I take x, then it maps to c times x. So this is x directional vector, and this is y directional vector. Okay. So in single variable case, the differential can be considered as a linear transformation. Now you can generalize to the linear transformation matrix, which is a differential of the multivariable function. But before we talking about in full generality, let's say we have M by N matrix A. Then it represents a linear map from Rn to Rm. Why? Because if I take V inside of Rn and take my V as column vector of n coordinates, then A times V, which is M by 1 matrix, can be considered as an element in Rm space. So I'm taking these Rn and Rm as a vector space, not just a space. These are the vector space. So whenever you have a matrix, you can think about the matrix as a linear map. And it's one thing that you have a matrix as a linear map, but the other thing is that you can interpret or give a meaning to this linear map. So in the differential of function case, there is a meaning of this linear map. It maps the velocity in the domain space to the velocity in the range space. This whole concept will be clear when you know the chain rule, or maybe not, but just I will keep explaining that, because this is the most important thing that you have to remember in the multivariable calculus, because that's the essence that you're going to use in the deep learning or artificial intelligence or any other algorithms, or in differentiable functions. When you solve a differential equations, you need a linear approximation, and you need understand why the differential is a linear map. So it's very important. So I hope that it answers the questions. If it's not, just let's wait out until we finish our chapter chain rule. Alright, so what is a chain rule? So here's the simplest version of the chain rule. So we have two variable function f, x, y, and we have a curve on the plane ct parameterized by ct. Now we assume that our function fxy is differentiable at the point x0, y0, and that's the starting point of our curve. And let's composite two functions, f and c. Okay, so c maps t to a pair of points, and we take that pair of points to the input of function again. So outcome is the z-valued function also. So we simply get a single value function f, which sends t to some value of function f. Then the conclusion is then this composition is also differentiable at the point t0, which gives x0, y0 in the parameterization c. And moreover, this is more important, the differential of f can be written as, of course, this f prime t0, a linear combination of x prime and y primes, and with a coefficient given by the partial derivative. Okay. So easy way to remember this is that we have a graph of function, say z equals to f of y, and we have a point of interest x0, y0, and I want to move along this direction, which is x prime t0 comma y prime t0. So instantaneously, okay? So in a very short time, I want to move my point x0, y0 to this direction, which is c prime t0. Now, how does the value of function change? So how do you measure the change of value of function? So how do you measure the difference of z? So if you enlarge this picture of a graph, then let me just put another page here. So it's going to be long. So if you enlarge, then this surface looks like almost a plane, flat plane. Okay, so let's say we have a flat plane, almost flat plane, and let's say we have this point as x0, y0, and our direction of vector, this c prime t, gives the same vector, these vectors on this plane. Okay, this is c prime t. So of course this c prime t on the bottom is t0, sorry. So t0 is the two-dimensional vectors, but I just lifted up to the three-dimensional vectors in the three-dimensional space. And we can decompose our difference of z into two parts. First, I can take the x direction and y direction here. So here we have x direction, y direction. So this part is xt and this direction is y prime t 0, sorry. So more specifically, this direction is x prime t0 comma 0, and this part is 0 comma y prime t0. Okay, so and see how much the value of z changes when I move my points to x direction and then y direction. So when I move along the x direction, the difference between the value of z, so let's see here, actually I should make this more dramatic, like this, okay. So that if I have z-axis, there should be starting initial z0, and here we have z1, and finally we have z2. So difference of z is approximately z2 minus z0. Okay, and you can decompose into z2 minus z1 plus z1 minus z0. So let's think about z1 minus z0 first. That's the difference when I move my point to the x direction in the velocity of x prime t0, right? So I only change the variable x. So when I change the only x variables, it gives the partial derivative, the ratio of difference of z value and the difference between the value of x gives the partial derivative. I only change the x directional difference. I only see the x directional difference of the value. So this gives fx on x0, y0, and see the difference. So we have x prime t0 times delta t. So actually this is approximate, so or let me just say delta x. So this length is delta x, okay, and these lengths is delta y. So this part is z1 minus z0, and how about this part? So z2 minus z0 is when we have a difference of y but x is fixed, and want to see the difference of the z value when I change the value of y. So that's the ratio between the difference of z and difference of y is the partial derivative of f with y at that point. But at here we are starting with this point, which is x0 plus delta x comma y0. So we slightly change our point and then multiply with delta y, right? And let's think about the difference of time again. So if you divide delta t, and also this is not actually equal because this gives only approximate change. So when we divide delta t on the left and right hand side, you get f of x. So this is also approximation. F of x, x0, y0, delta x over delta t, and fy, x0, delta x, and y0, and delta y, delta t. And then let delta t goes to 0 because we are looking at infinitesimal change of time. So this delta z over delta t becomes dz dt. And now if I make this time sufficiently small, this approximation becomes actual equality. So we have fx, x0, y0, dx dt. And then this part also disappears. Delta x goes to 0 because, so therefore fy, x0, y0, and dy dt. So what is dz dt? So we are sending point x0, y0 along the curve. So actually the curve was something like these curved line, but instantaneously we had a velocity c prime t0 here. So this straight line, the straight line on this flat plane, is an omnion approximation of a curved line inside of a surface, but that's fine because we're going to send our dt to 0, which becomes actually the same if you take the infinitesimal change of t. So this z is simply c composite f. So therefore z ddt is nothing but ddt of small f composite c. So therefore that's df dt. Okay. And by the way, this is the differential at t0. Okay. So this expression is exactly the same expression in our theorem. So f prime t 0 is given by dz dt at t equals to 0, and rest of the part are the same. So this is the easiest way, or geometrically intuitively way, to understand the chain rule. But this is not actual proof of chain rule. We need a long proof, mathematical proof. However, sometimes looking at the proof of our mathematical theorem does not help to understand the theorem of nature of the theorem. So because we don't have much time, and also it's more important intuitively understand the chain rule instead of understand the logic of the proof, we're going to skip the proof here. So if you are interested, you can read my proof in the slide or in our textbook. The reason why I chose this textbook, it's really rigorous. It contains all rigorous proof of the basic facts on calculus, multivariable calculus, unlike other textbooks. So you can read the textbooks for rigorous proofs. But let's skip that for now. All right. So here's another remark on the chain rule. So let's rewrite our chain rule here. So if I take the composition of f and c at t0, the different derivative becomes fx c t0 times x prime t0 plus fy c t0 times y prime t0. So in other words, this is simply can be written as x fy vector at ct0, okay, dot product, the inner product, with x prime y prime. In other words, if you have a parametric curve, the velocity vector is the vector whose components are the derivative of each component functions. So this part, the second part of the dot product, is c prime t, and the first part of the dot product is the gradient of function f at ct0. So you can rewrite your chain rule as this equation. Okay. So what does that mean? So it means, just I'm going to read out this remark, the rate of change of the function to the direction of c prime is given by the inner product of gradient vectors and this vector. Okay. Again, so if you want to find out the rate of change of value of function to some direction, you only need a gradient of the function and the velocity that you're going to take the rate of change, and you just multiply or just take the inner product between two vectors to get the rate of change. So when we talk about the directional derivative, of a function at some point x0 and y0, or maybe I just use another page here. Do I have? Okay, so let's put another page. So let's say we have directional derivative. So the directional derivative can be written as the inner product between gradient and the vector u. But let's try to see why is this true. So we have 1/t of f composite c t minus f composite c t0, where this ct is nothing but just a straight line which maps x0 y0 to c t times u. Okay, so and then what you see is nothing but the derivative of two composite function f and c. So now in other words, I can just take c prime 0 here. So by the above observation here, we have this is equals to gradient of f at c0 and inner product with c prime t. So if you have this linear map as a parameterization, when you take a c prime t0, there are only one t appears in this formula, and that t has order 1, the degree 1, so it's a linear map. So what we have left is always a constant vector u. So this is equals to f c0. In other words, c0 is equals to x0 y0 times inner product with u. So you can easily compute your directional derivative using the inner product. Okay, you don't have to go through all the definition of limits. All right, and these are all the benefit of chain rule. All right. Okay. So one other thing about the chain rule is that you can actually have two vectors, and you can composite two vectors and find out what happens when you change your function to the direction of this composition of two vectors. For example, if you have a gradient, as I said, you can consider your gradient as a vector field sending a point in the two-dimensional plane. Sorry, there's a missing 2 here. The vector. So this part is sorry. What? So this one. So what I'm talking about is you specify the point x0, y0, and you specify a gradient vector with scalar components here. If you have two-dimensional vector v1, v2, then you simply take the inner product with this vector v, saying that fx, x0, y0, and fy, x0, y0, with v1, v2 as the corresponding vector. Let's say u here, and this computes as fx v1 plus fy v2. So your sorry, it's not a vector, sorry, so this is a scalar. So this is a number in real line, and this gives the linear map. So linear map means the the vector operations consist of scalar multiplication and vector sum preserves on the range of the value of this linear map. So if you have two vectors, v and w, you can decompose your inner product. So basically you have to take the inner product here, the inner product. But you can either take the inner product with the sum of vectors, or you can take the inner product of each vector separately and then add them together. So what we are saying is that if you have c prime 0 as v plus w, and we know this f prime, and we know the gradient at c0 at direction of v and fc0 inner product w, then without knowing what actual gradient is, you can find your gradient inner product with c0 as simply a sum of these two values plus this c0 w. Okay, so I'm saying that we assume that we don't know the gradient itself, but we know the inner product of the gradient and some component of vectors. Then we can find your gradient inner product with original composition of vectors by taking the sum of two scalars here. Okay, this means sometimes we do not need to know entire gradient to find the rate of change. At certain direction. So why is it important? Why do I talk about this part? So mathematically, if you have a formula, of course you can find the gradient by taking partial derivative. But if you want to apply this kind of theory into practice or some experiment, sometimes it's impossible to find the entire formula of a function which determines your system. Okay, so for example, you have a complicated machine or complicated environment or complicated situations, and there are thousands or hundreds of variables that you can think about to describe this situation. It's simply impossible to find the formula, all the correspondence between the variables and the functions that fits into the description of a environment. The best way you can predict what will going to happen is that you take one variable each time and change that variable and see what happens in the outcome. Okay, so for each variable you take the small difference of the variables and then records the outcome. That means you're recording the partial derivatives in that direction, or you're taking rate of change to the that direction. If you want to find out what happens when you change your variable in the same time as if you're changing the variable in the direction of composition of two vectors, or let's say here's one direction that you observe the outcome, and here's the other direction that you observe the outcome. You want to find out what happens to this direction. For example, this is not simply v1 plus v2, but you can compute your linear composition with v1, v2 with some coefficient c1 and c2, and you want to observe what happens when you move your point, you move your variable into the direction of v. Then this rate of change, what happens is that simply you take the results, what you obtained in direction of v1 and v2, and take the linear combination with the same coefficient c1 and c2, right? And then this c1, c2 can be arbitrarily, so you can describe entire behavior in two-dimensional vectors. You can now fully know what happens in the system when you move your points along inside of the plane spanned by v1 and v2. If you want to know what happens in 3 dimensions, then you just add one more axis or one more direction which is independent to v1 and v2, and so on. So in practice, you don't try to find the entire formula function. Most of the time you're going to see approximately what happens to the environment in the certain direction in infinitesimal time. So that's why we have to understand the gradient and the chain rule. Okay. All right. So that's the case when we have a parameterization on a two-dimensional plane and the function on two-dimensional plane. What happens, we have a slightly more general situation. We have a same type of function f which sends r2 to r. So basically this function, it looks xy sends to z. But we have another function, not a parametric function, but it's just called a transformation. It sends points in 2D-dimensional plane to two-dimensional plane. So it sends a point u comma v to x comma y. So x and y are both function of two variables u and v. I simply give a same name for those coordinate function as x and y. And let's pick a specific point. When u and v are u0, v0, we get x0, y0. So in other words, this is the situation we have. Let me put another page. this is our R2 UV. This is our XY in R2. So let's say our CT changes in UV plane from U0, Y0, then it should move along this XY, along different direction, along this X. So X composite CT move along this XY plane from X0, Y0. Okay. Now I want to composite again, because function f is defined on XY plane. I composite this function x to f to get a real number r. So what I want to know is what happens when I change my u0, v0 to u direction and v direction. And I want to know what happens to the value of function, value of the final value r. Okay. So the result says there's also the concept that this composition at large f is also differentiable, but the final result is, what important is that the positive derivative of this new function obtained by composition is written as these and these. Okay. Let me rewrite this expression. So it's a not good looking expression, but if I write my partial derivative in curly delta notation, then the first one written as del f del u equals 2, and I drop all the points here, coordinates of points for simplicity. What I get is this expression. So you see, I want to take a positive derivative of u, so it appears on the bottom, but in the middle we have an intermediate variable which connects the variable u to the value of function, which is x and y. So we have x, y, x, y, x and y appears in the between. So it's not intuitively correct, but easy way you can remember is that you simply kind of eliminate this intermediate dx and dy, so that you finally get trying to compare the difference between the function f and the difference between difference in the variable u. But that's not the recommended way to remember the formula, but just this one. Just think about this formula itself. And then the second part is similar. You just replace u by v. So you have del f, del x, del x, del v, and del f, del y, del y, del v. So you simply lay out all the intermediate variable and then make it into summands in this right hand side. Okay, so we have two intermediate variable x and y, so we have two sums. If you have three, you have three sums. All right, the proof is actually easy. You just simply looking at the each partial derivative separately. So trying to think about fu. So this is just the idea of a proof, not entire proof. Let me give an entire proof here. So fu at x0, y0 is simply you're taking a derivative, partial derivative in terms of u. So you can take f of x0 t and y0, because I'm looking at what happens to the value of function f when I change my points only to the u direction. So this is u0, not x0. And let's rewrite my composition. T0 and F composite C, X and U plus T V here. Let's rewrite that in terms of X and Y. So F of X U0 plus T comma V0 and Y U0 plus T and V0. Right. Okay. So from here, I want to use our original, the first chain rule that we explained in the beginning. Right, so yeah, so let's think about this way. So I'm going to give a different name for these parts. So let's say this will be denoted by, let's say, AT, okay, and this will be denoted by BT, okay. So this is equals to ddt of t equals to 0 of F composite C of t, where this CT is equals to AT comma BT. So I define these expression X of U0 plus T comma V0 as AT. Therefore, X is a real values function, so AT is a single variable function. So it fits to the situation of the first chain rule. So when I do this using the chain rule, the first chain rule, what happens is it's same as F C0 times C prime 0. Well, this is same expression as Fx C0, which is A0 B0 times A prime 0 plus F of Y A0 B0 and B prime 0. Okay, so what's A0 and B0? When we have t equals to 0, we get X of U0 V0, right? We define that to be X0, and Y0 is Y of U0 V0. So simply I can rewrite this as X0 Y0. And what's A prime? So when I take the derivative of A prime, I'm taking a partial derivative of X. So again, A prime 0 is ddt at t0 of X of U0 plus T free 0. Right? That's a definition of partial derivative of X in terms of U, right? So we have dx du, right, at u0 v0. So we have xu of u0 v0, and the same thing for the rest of the part. We have x0 y0 and xv instead. So here we have b prime 0, which is ddt of t equals to 0 of is it y? Oh, right, sorry, that's not x3, so this is y u. So y of u0 plus t of v0. So you only change the direction of u of function y, you get partial derivative of y in terms of u at u0 and y0. Okay. So that's the first part, this part, number one. And second part goes exactly the same. You replace u by v. All right. Okay, let's look at another remark. So that actually gives the intuition of what actual chain rule says. Not geometric, but real meaning of the chain rule. Let's rewrite our chain rule, the first chain rule, using the matrices. Okay, so for example, I defined my large F to be composite of small f and c, and we wrote that my large F prime is equals to some linear expression, but I can rewrite that as here. So instead of choosing a specific parameter t0 or specific point x0, y0, I just put everything in the variable, okay, for simplicity. So I can rewrite my f prime as a matrix product of these two matrices. The first one is the gradient of f. How about the second one? That's c prime, right? But look at this. F is a composition of f and c. So you see what's happening here. So we have a composition of function. Derivative of composition of function becomes the multiple of differentials of each functions. This multiple is not an inner product, it's an actual multiplication, because you see, in the most general definition of the differential of a multivariable function, this f is has two independent variables and one dependent variable. So therefore df is what? 1 by 2 matrix. Okay. How about c? So in c we have one independent variable and two dependent variable, right? So we have dc as 2 by 1 matrix. Okay. So we can actually multiply these two matrices in a row. 1 by 2 times 2 by 1 makes sense. So this is 1 by 2, 1 by 2, and this is 2 by 1. So these two cancels out, and the result is 1 by 1 matrix, which just becomes a scalar. Same thing as the derivative of single variable function large f. How about when we talk about the second version of the chain rule? We compose this f and the transformation x. So the transformation has two independent variables and two dependent variables. Therefore, the derivative differential is 2 by 2 matrix given by this. So this is differential of x. Okay, and this is the gradient, or you can simply write your gradient as differential, just dx. Okay, same as dx, df. So what it says is that your df multiple, so this is actual multiple of matrices with dx, is given by df, but f is nothing but composition of x and f. So you see, now we have also the same kind of rule. That chain rule says that the differential of composition of function is same as matrix multiplication of differential of each composite of functions. So note that the gradient can be written as 1 by 2 matrix, and same, we're actually, the last part says the same thing I just said. So summarize, let's look at this one. So this is the most general form of chain rule. So we have a function which sends n-dimensional space to m-dimensional space, and we have another function which sends m-dimensional space to l-dimensional space. So what happens is I'm sending a point in Rn to a point in Rm by function f, and then sends that point to a point in Rl. So this is the final point. Okay, I want to take a differential of this map which sends P to this point. Then that differential is same as matrix multiplication of two differentials. One is from G and the other is from F. This is matrix multiplication. Since we composed F with G, the order of matrix multiplication must be preserved as F and G. The order of multiplication must be preserved. So you have to remember two things. Okay, and also note that we are taking a differential of G at the FA. So here I used A, so here let's use A instead. So since we are taking a differential at here, not A is not in the domain, even not in the domain of G. So we are taking a differential at the value of function f. Okay. So that's the thing. But you see, this exactly is the same as when you take a composition of two single variable function and try to take a differential. So for example, you already learned that the DDT of your two function, if f and g are single variable functions, this is equals to df dt times dg dt. But this part evaluate g, let's say gt, and this one evaluates t, right? This is exactly the same generalization to multivariable function, right? So here is an example. I think that will be the last part of our lecture today. So this t sends polar coordinates to the Cartesian coordinates of two-dimensional plane. Let's suppose that I choose my large f to be composite of function f and this transformation. Then this fr, f theta, looks this way. So that's in the matrix form, we can rewrite this one. So even though you might not fully understand what I said about the chain rule, you must understand right now how to take the partial derivative of composition of two functions. So this is one example, or the most famous example that you're going to use many times later in the course. So think about your FR first. By definition, this is equals to, by notation, this is equals to FRDR. Let's use the standard way of memorizing how to take the partial derivative of composition. First, you take the partial derivative of outside function, which is small f, and what comes in the bottom is the intermediate variables. So here we have intermediate variables of x and y. So t sends r theta to x comma y, and f is a function on x comma y, so I need x here. We are taking a partial derivative of r, so r comes to last, and fy and del y del r. Okay, so what, I don't know what these are, I just put it as fx, but I know what these are. We have formula of x in terms of r and theta, so we have fx cosine theta and fy of sine theta. So when I take a partial derivative of these expression by r, I take theta as a constant. Okay, so this is the linear expression of r, so it's a 1-degree polynomial of r with the coefficient cosine theta, so I have cosine and sine here. How about f theta? So we have del f del theta, which can be written as del f del x del theta, and del f del y and del y del theta. So we have fx, and now we are taking a partial derivative of this formula by theta, therefore I'm taking r as a constant, so r minus sine theta plus fy of r cosine theta. So we have two expressions for fr, f theta. I can rewrite that as a matrix form, but why we're taking this kind of expression is that f, if you're looking at f as a function, it sends r2 to r, right? It has two independent variable, one dependent variable. So the differential of large f is 1/2 matrix. That's the differential. So it sends r theta to some real value fr theta, right? So that's df. And how about this part? So this is the small f, okay? And how about this part? This is d of transformation t. So therefore, what I wrote in the matrix form is df is equals to df times dt. So I omitted all the points, value of points, but if you really compute what happens at this point or that point, you have to put a coordinates, you have to plug in numbers to r theta and xy. But when you plug in there, when you compute df, you have to plug in the value of r and theta, but when you plug in number in df, you have to plug in number for xy, which corresponds to the value of rx, which means that you have to plug in value of xy obtained by compute t of r theta. Okay. This part you can just simply plug in theta and r, okay, all expressed in r and theta. Alright, so I think that's it for today. The next part I will describe more general concepts about the chain rule, but mostly I think will be the problem solving. So in the last part of the problem talks about the Laplacian and how to express that in the different coordinate systems, and there are also generalization to the three-dimensional coordinate system, and these kind of transition is used mainly in the physics, and also maybe you already saw that in the physics course in electronics, but I will do this in thoroughly here. So that's it for today, and there's an announcement. 제가 저기